I think we shall start now. The participants have joined. Professor Seferi, so very good morning to you. And I request all the participants to please be attentive and don't unmute yourself in between the class. If you have any query, please post in the message box. I will convey to the Professor Seferi. And also the feedback form will be shared in between the lectures, anytime in between the lectures. So please keep your eyes on that also. So I request Professor Nariman Seferi to continue with his lecture. Sir, please. Okay, wait. I'm doing it.
Yes, you already unmute me. Can you hear me?
Yes, now I can hear you.
Okay, excellent. Thank you very much. So do you see my screen yet or not?
No,
Share
it's not
screen.
visible, sir. It's not visible as of
Okay,
now.
okay. I am going to again do that. Okay, now you should be able to see my screen.
Sir, please.
Okay. Okay. Good evening, everybody over there in India. And what I'm going to do today, I'm going to, as I said yesterday, will show you a 5 minutes, less than 5 minutes presentation by Siemens, which talks about the pump efficiency. It's a collaboration that we do that with that company, and also Purdue University developed that. And that talks about pump and motor efficiency and some very basic equations. Then after that, I will show you a couple of applications of the hydrostatic actuation. Then after that, I will talk about the faults that happen in hydraulic system, including hydrostatic actuations and fault-tolerant controls, optimization for a better control, and also condition monitoring using Raspberry Pi on a real application. And I will show you some video as well. And then we will wrap it up on that one. So given that, I would like actually to start the video. And if you do not hear the words from the video, Ajit, please let me know. Thank you.
Please go ahead, sir. Sure.
Yeah. It just started.
Welcome to module 2.2 of the course. In this module, we will learn about the actual performance of pumps and motors and how to quantify this actual performance. In this process, we will also learn about various losses in these machines that leads to deviation of machines' actual behavior from their ideal worth. In last module, we covered the ideal behavior of positive displacement machines, which are pumps and motors. A quick reminder, pumps and motors are the same types of machines. The difference is in the direction of energy change. For pumps, the given displacement and speed, the ideal flow is just displacement times speed. For motors, if flow through the motor is known and its displacement is known, then the ideal speed of the motor is just flow over displacement. In actual pumps and motors flow, there are volumetric losses like leakage of fluid from high pressure environment to low pressure environment. Due to these losses, the actual flow given by the pump is smaller than its ideal flow. Due to same losses, the actual speed of the motor is smaller than this ideal speed. So, we define volumetric efficiency of pumps and motors like this. The volumetric efficiency of a pump is defined as ratio of actual flow and ideal flow, where ideal flow is simply speed times displacement. Here, E stands for effective, which means actual. For motor, the volumetric efficiency is defined as ratio of actual speed and ideal speed. Ideal speed is written as flow over displacement. We also learned in the last module that if you know the displacement and pressure difference across the pump, then the ideal torque required by the pump is displacement times pressure difference. Similarly, if the torque output of the motor is known and the displacement of the motor is known, then the ideal pressure difference across the motor is torque or displacement. In actual machines, there are balances like friction between components. Due to these losses, the actual torque required is higher than static torque. Similarly, the actual pressure difference across the motor is higher than this ideal pressure difference. So we define the hydromechanical efficiency like this. For pumps, hydromechanical efficiency is the ratio of ideal torque required and actual torque required. For motors, it is the ratio of ideal pressure difference across the motor and actual pressure difference across the motor. Now that we have defined volumetric and hydromechanical efficiency, the total efficiency is just the product of volumetric and hydromechanical efficiencies. In the expression of total efficiency for the pump, the numerator has product of pressure difference and flow through the pump, which we learned in last module is the harmonic power generated. In the denominator, we have the product of torque and speed, which is a mechanical speed. So, total efficiency indicates the dynamic mechanical efficiency by the pump into the harmonic energy. The expression for total efficiency of motor is exactly opposite, which makes sense. Says the motor is hydraulic energy. So, the total efficiency of the motor is what amount of hydraulic energy is converted into mechanical energy. Here is a small example problem.
Okay, can you hear me now? Am I audible?
Yes, Professor, you are audible.
Okay, thank you very much. So I'm going actually to share my screen for the other part, which I will be continuing talking about a couple of applications of the hydrostatic before I go to the condition monitoring. So let me just bring it to the point that we stopped, and then we will talk about it. Okay. So I'm going to share my screen right now. Okay. I hope you can see this one. And then we will start. So we talked about hydrostatic actuation, and you should be able now to see my screen right now. And then I will show you a couple of applications that is been happening in different places, including our own. I'm not sure whether I will show you this one, our own, but I will show you later on. One of the application of the hydrostatic actuation is on excavator machines. And if you see this machine here, this machine is an excavator machine, is located or used to be located at Purdue University, and it's an experimental system, and it has three actuators, A, B, and C. A is for the boom, B is for the stick, and C is this hydraulic for the bucket here for that. And as you can see, each of these single rod linear actuators A, B, and C are controlled by a pump motor arrangement. And in this pump motor arrangement, the system uses a circuit, which this circuit pretty much are the same. This one, this one, this one the same, and each of them independently controls each of the links that we have seen here. So there is one motor that runs through the gear and runs all these three pumps. And also, one thing you can see is what we call it energy storage here. So whenever any of these actuators serve to help the motion, normally it's this boom motion because the boom goes up and down. And when it goes up, you need to apply energy. When it's going down, you should be able to use the gravitational force in order to bring it down. And that gravitational force also can run this pump. And this pump can go back, actually, and runs this pump and save energy here. And once you have energy saved there, then you can use this accumulator in order to run some other application. This has been used very clearly in the system, and it's working. Another example, which is also very nice, and I enjoyed actually looking at this diagram, is the wave energy extraction. Wave energy extraction uses fluid power in order to extract the energy. And if that's the wave or the water, these floaters are on top of the water, and as the water moves, the actuators here start to move back and forth. And as they move back and forth, the energy efficiency is translated into the displacement of this actuator. Now, there should be a way in order to extract this buoyancy force that causes this actuator to go up and down into saving energy here. And the diagram or a circuit for that is quite straightforward, but very novel and very nice. So let's see how that one works. Let's look at this figure. Suppose this wave buoyancy tends to move this cylinder up. When it pushes up, the fluid is forced to go into this direction and opens this check valve and starts to save the energy in this accumulator. And of course, some of this energy goes through here, through the motor, and the motor runs this generator. The flow back, if needed, can be saved here. And it goes back through this line, through that line, through this check valve, and it goes back to this side of the actuator. Remember, when you start to move this actuator up, you are basically needing some fluid in this direction. So the fluid goes back here. So that works quite well in this case, which is very nice. Now let's look at when the buoyancy or the wave goes down. and this buoyancy force tends to move this actuator down. Pretty much the same. When it pushes down, the flow goes in that direction, goes back to this one, stores in this pump, or goes and runs these pumps and the generator to save, to produce electricity. Goes back here. Some may go over here if it's needed, or later on for leakage. And then again, the flow goes back here. So the design is quite nice, and it seems to be working, and it shows the applications of the hydrostatic actuation in these cases. So let's move to the next one, which is about the condition monitoring. In this case, I'm going to, let me see. I have another application. Let me just see what happened here. Okay, so I'm going to share my screen again here. And you should be able to see my screen. If you don't see it, Ajit, let me know. And this one is another application for aircraft systems. And the information I have, this is a typical one that is being used, I guess, for Boeing. They might have changed the design, but this is the information I've had. This one is for aileron. And this is a hydrostatic actuation for a double rod cylinder. And it's quite straightforward and nice, very practical, and I enjoyed looking at it. If you look at that, you will see that we have a power electronics, that this one is responsible for controls. This one runs that motor. The motor turns left and right and changes the speed. So you can actually change the speed of this motor, and this motor, the direction. You also change the flow going in this direction or in the other direction, vice versa. Depends on how you are going to do that. So in this position, for example, we want to rotate the motor here. The pump will flow here. Case, the pump pumps it in this direction. This orientation of the valve V3 allows the flow goes here. The flow goes there, pushes against this cylinder, and the flow comes back here. Comes back here. So what you need to do, you need to visualize the role of this valve V3. And this is basically a directional valve. So by changing the direction of the pump from this side to this side, I can actually change the direction of the flow. And I can apply the flow here, and the flow goes back there. And then now I can move. I can move my piston in this direction. And of course, you will see the role of this valve 3 is that if you want to disconnect completely this circuit from this circuit, from the other circuit here, all you have to do is to shift this valve down and connect this portion, which is also very practical, and it does a good job as well. Again, there may be some visualization to take a look at it to see when you move this valve down, what will happen. You basically connect this and connect that and disconnect these two circuits from each other. So that is another application of the hydrostatic actuation. So I'm going to stop sharing this one, and then I move to the next step, which is, if you bear with me, I'm going to go to the next lecture, which is about condition monitoring. And then what I'll start to do, I will start to talk about, I'll start to talk about fault-tolerant controls and fault detection and condition monitoring on this one. So let me again share the screen for this for you guys. And I'm sharing the screen. You should be able to see that. And what I'll do is that I will talk about the fault-tolerant control for hydraulic actuators, and I will show you a couple of videos also showing that how we are using this system. It is very important to know that any system, any mechatronic system is subject to faults and also is subject to some non-idealities that can happen, and also is subject to some parameter variations. All these contribute to the system may not work as best as what it used to work. And as a result of that, you need to be sure that we need to be sure that we are coming up with a controller, that this controller is robust to uncertainty, non-idealities, and some certain faults that can happen on the system. So this is what is a subject of what we call it fault-tolerant controls in hydraulic actuators, because hydraulic is our focus of the work. So what I'm going to show you again, I go back to the flight control system because it's a very sensitive system in terms of being robust and fault tolerant as much as possible, and for the safety. So I will show you, I will explain what we need to know on this one, which is typical in other systems as well. In a flight control system, again, as you see, the control surfaces are controlled by hydraulic actuator, typically. But this hydraulic actuator is subject to what we call it fluid leakage, and we will talk about that. And the leakage can happen between the cylinders, between the chambers of the actuator. It can go outside the actuator, or it could happen on any line, connecting line. The other thing that is important is the air and water contamination. In your lecture 1, Dr. Ajit mentioned about the water contaminations, air contaminations. Those change the bulk modulus of the system, and changing the bulk modulus will affect actually the parameter of the system, and as a result of that, the behavior of the system might change. And that you have to be able to control that. Incorrect pump pressure. Sometimes the pump pressure may not be able to produce the pressure that we need in hydrostatic, of course, due to certain non-idealities and including the leakage. And that's what my first part of the lecture was about, the efficiency and calculation of the efficiency. Plugged filters, of course, every time you have cavitation or aeration and cavitation, that might cause some imploding and erosions of the components, and those components might make the oil dirty, and as a result of that one, it might clog the filter. Friction. As the system runs, you will see that the changes in the mechanical parts that can affect the friction. And of course, valve and sensors or electrical failures. If there is a valve you're using, might fail. If you are using a sensor, the sensor may not be able to produce some proper accurate results or something. So you will see that all this contributes to that. And what we are interested to design controllers that these controllers are tolerant to faults and uncertainty in the system. So let's look at this next case. This is the plant that we are considering. Okay? And this plant is subject to certain uncertainty. Uncertainty can come from parameter variations of the system. As I said, any system, if you write the dynamic equations, has some parameters. That includes, for example, the friction coefficient, that includes the bulk modulus, and all these changes with time and as the system changes, as the system runs. The system is subject to temperature variation that can cause changes in the bulk modulus and other things. What are the other uncertainty on the systems? Effect of faults. Faults can cause as a disturbance or can change some of the functionality of the system, and that also causes the uncertainty in the plant. And also the other things is the nonlinearity. If you design or if you look at your plant as an equivalent linear system, this nonlinearity can change parameters because you represented this nonlinearity into the linear system. So now we have a system that we can model it, but is subject to a lot of uncertainty. And what we are trying to do, we're trying to control this system. We want to control the system in spite of all this uncertainty that that system has. As an example of the uncertainty is the leakage. And as I said, the leakage can happen to outside or it could be internal leakage. Internal leakage is a typical fault and can be quite serious in this case because you do not see it, but it happens as the seal here starts to fail, and then the actuator loses some of its power in order to actuate against a load. And sometimes it's not noticeable because we close the loop and we make the system to work as best as possible until the whole thing fails. And all of a sudden the actuator will fail. So these are the things that you do not want to happen on a safety critical systems. Of course, for example, in this case, the leakage, the reason I just wanted to show the nonlinearity a little bit, the leakage can be programmed as, can be formulated as a coefficient, which is basically this area is the area of the opening and is subject to a square root of the delta P. And normally the leakage area could be between 0, which is a normal, to 1 millimeter, but this is a typical one. I was hoping actually to explain a little bit about this one that causes nonlinearity. And of course, when you linearize that, then the system that you will be dealing, your P, remember I told you that the P is presents the system, and under uncertainty. And we can represent that one in this form, that many of these parameters are due to leakage, due to changes in the variation, dynamics, and the gain of the system. So this plant is subject to variation of these parameters that can come from linearization of your system, can come from uncertainties of the parameters that you are using, and can come from the fault. And that fault can contribute to some of these parameters. So you have a system, and this system is represented by this linear system, but this linear system is subject to uncertainty on these things. And this uncertainty has to be taken care of when you are designing your controller. So what we are looking at when we design fault-tolerant control is that we look at our uncertain plant, and we are trying to come up with what controllers and what kind of filter we want to apply to these two. These are the design, 1 and 2 are our design, in order to make this uncertain plant to behave the way we want it to behave. That means if we send a command to that system, we want this one to also behave nicely, and regardless of how much uncertainty we have on this plan. First, there should be limitations of the extent of the uncertainty we put, because you cannot have a system, a very, very uncertainty system that works all the time. So these are basically the design for us. And normally, if we have this system, and this system subject to uncertainty at a certain frequency may not be only a point, but an area. An uncertainty of the system will manifest itself by this plant to be anywhere over here. And this is the magnitude and the phase of your plant. And of course, if you have different frequencies, and this is the frequency is nothing to do with the natural frequency of the system, with the damping that, with the omega n that I showed before. And here, I just wanted to emphasize that, for example, at a certain frequency, if you do not have any leakage, your system will be here. If you have a medium leakage, your system template will look like this. If you have a large leakage, your system template will be here, and these are medium small and medium large leakage. So you will see that the leakage can move your plant in different locations. And of course, controlling this requires certain attention, controlling that requires certain attention on that. The other important thing that is important is that a controller, which is not a fault-tolerant controls, may behave differently when you have a certain fault. Let's look at that. Suppose you want your system to behave within this limit, regardless of the fault, which is not bad. You know, this is what we decide to have. If you do not design a fault-tolerant control, a normal controller can produce this one. If you design your controller for a normal condition, it will be like this. This is a black line here. But as you increase your leakage, you will see that a smaller leakage will make the same system that used to work here now starts to work here. And as you increase the system, the leakage, you will see that your system will behave here. And if you increase the leakage, you will see the system behaves here. What does that tell you? That tells you that if you design your system, regardless of the internal leakage, for example, fault. If the fault happens, the system that used to work here now starts to work here. And what does that mean? You basically are not following this bounce anymore. And at the same time, the system becomes sluggish, some delay, or let's just call it delay. Here is happening, and it's very, very slow. So if you design it here, and if you want, it happens to work in this direction, in this line, because of the appearance of the leakage, then the system may not be performing good. And this is not what we want to see in, say, safety critical operations, including the aircraft systems, because we want the system to be running as best as possible, regardless of the fault, until the fault is diagnosed. Okay, so this is the fault tolerant controls. This one is the ideal case. What we would like the system to behave in between these two lines, and we want the system to perform regardless of the leakage that we have, ideally. So we need to design our controller so that the controller, one single controller, can work over here. Or we may want to have a number of controllers, and each controller respond to a certain leakage. And of course, this is what I'm going to show over here. Of course, we have done a lot of more advanced controllers on that, but this is a very simple case here that we want our plant, which is subject to the fault. And what we do here, we look at the input and output that goes to this plant, and we do the fault detection, in this case for the leakage. And then we will decide the level of the leakage. And then we come up with controllers that these controllers each responds to each level of the fault. And each of these controllers also come with their own pre-filters. And once we have this one, we can switch between these two controllers. Now, these are basic controllers that work for each level of the fault. And the fault happens, then we need to have this fault detection system to decide which controller to starts to kick in. Of course, there are more improved ones that I do not want to go into that direction, at least for this one, that you only have one single controller that is robust to all type of faults, because sometimes detection of the faults can also be a little bit challenging. Each one of them, they have their own challenge. If you want to have a different controllers for different fault, then you need to come up with the fault detection and isolation that by itself has challenges. If you do not want to go into that direction and you want to have a single controller here, then it has its own challenges. Then the controller has to have low bandwidth, not to be responsive very fast to things, and at the same time also be tolerant to different type of faults. But what I'm going to do, I'm going to focus on multiple controller that is relying on the fault detection here. So quickly, again, we want the system to follow this one. This is a closed loop system, VG, and we want that to be limited to 1.0 less than this, which basically tells us that we want the system to respond as best as possible for various omega here. But at the same time also, we want this system to follow, to behave between these two. That means we want the system to follow between these two limits, upper part and lower part of the system. We are using a fault-tolerant control of quantitative feedback theory on doing that. Quantitative feedback theory was developed by Horwitz and Hoppus. They worked very diligently and with many graduate students in order to bring it up to this level of the control. And we are very fortunate to communicated with Dr. Horwitz before, and we learned from their experience And also we use that system in order to design a fault-tolerant control. Basically, in using a quantitative feedback theory, you decide on certain limits. This is your uncertain. This is your system. These bounds are based on the uncertainty and everything else, and you do want this system at a certain frequency to be upper or closer to this point, to these limits. So what you do, you come up with a controller that this controller moves this line to this line. Now this satisfies all the conditions that we want. So you see the beauty of the feedback control is to make your forward path system or your open loop part to look like this. So we have control on this controller to make my initial uncertain system to now look like this. And that is the beauty of design of the controls. So once you have your controller, then you can actually implement that one. We came up with controllers for various type of things. And if you remember, I talked about various controllers. In this case, various controllers, controller 1, 2, 3, 4, 5. So we need to come up with a method so that we can choose which controller to run. And this is based on this one. The control law switching tells us that use all the controllers. In this case, we are using 4 controllers. 0, 1, 2, 3, I think it's 5 controllers. 1, 2, 3, 4, 5. 5 controllers. And 0 to 4. And then each control signal sends a signal. But what we do is that we weight that control signal. So that would be our controller phi. So it will be like omega 0 U1 plus omega 1 U0 U1 plus omega 4 U4. So it's depending on whether we are normal situation or we have a very high leakage, then we will put more weight here or more weight there. How do we do that? We use in this case, we use a kind of a fuzzy mapping here. So if the system is no leak, the weight we give to the control is 1 over here, and the other weights are 0. If we are small leak, depends on where we are, we might give the weight to 1, or we might be somewhere over here in this region that we might give a weight of omega 1 and omega 2. For example, here we might say omega 2 is 75% and omega 1 is 25%, and vice versa. Very straightforward, but very diligent and is working quite well. So what we do, we decide our fault, what level of the fault we have, and it depends on where we are. Then we will decide, on the contribution of each control. Now look at this system. This system is that when we are using switching controls, as I explained, and somewhere here, I guess it's somewhere here, I apply a certain fault, which my fault is going to be the leakage. Let's look at the controller that we have designed here. You will see that once the fault happens, the controller may misbehave a little bit. but still switching controller kicks in and still makes the whole thing runs as smooth as possible. Of course, when you compare this part with this part, you will see that the system may not be exactly doing what is as before, but still does a good job. But now look at if you only use one controller that works under normal condition and it's not fault tolerant, as soon as we start to apply a leakage here, you will see the system starts to deteriorate, create a steady state error, which takes a time, to reach. And the system performance is very, very slow. This is not good. You don't want that to happen in safety critical situation, but this is much better than what we have over here. So let's try, and this is, you will see that what's happening over here. You can compare these two responses. So if I ask you which one of these response, this one or this one, you like most, of course, I hope that you guys agree with me that this one is the one that you want to apply. Now let's look at the controller switching. The switching controller, the first system that we have, the control signal looks like this. For the normal controller, it looks like that. Compare them together, and you will see, in fact, that the system control signals pretty much the same. We are not applying too much control effort in both cases, especially in switching controller, but you see the changes are quite subtle. And these subtle changes in the controller will make a big difference. So really, we are not putting too much burden on our controller and control effort, and yet we are making a big difference on the response that we are dealing with. Let's look at our experimental test rig. This is what we call it hardware in the loop simulator, that we are flying an aircraft. And this one has all and full everything, basically, that you have the entire aircraft dynamics into the system. But one thing that we have is that we put the one actuator that can emulate the left aileron of this control surface of this aircraft here. So that's what we call it hardware in the loop simulator. So everything, the simulations is on computer except for one actuator which is running here. But the good thing about that is that, and also, of course, this actuator is subject to load because all the aircraft systems, control surfaces are subject to the load, and this load is coming from the drag and lift that applies to the control surfaces that we need to create that one so it interacts with this system. But the good thing about that is that we can produce every type of faults that we can see in an actuator here. So I can go manually apply an internal leakage or external leakage or changing the filter clogging or pump functioning, and then we will see that those faults can affect the performance of the aircraft. Now I'm going to show you this video. And this video shows the aircraft running and all the parameters and everything we can see here, and here moving. And of course, one of the hydraulic actuator is running. Now, let's look at one case. In this case, I'm using fault-tolerant control on this aircraft, And while this aircraft is in the air and we are flying it, then I go there and apply a certain fault, internal leakage to the system. You will see that the system malfunctions, but my fault-tolerant controller realized that one and right away starts actually to fix, or rectify, the response. As a result of that, the pilot or the person who operates this aircraft can actually control this aircraft much more faster and easier to do that. Let's look at it to see how it works. So this aircraft right now is working normal, and somewhere in between, if we introduce internal leakage, a very severe internal leakage, you will see that the system might have a little bit malfunctioning, but because of the fault-tolerant controls, this effect is very minimal, and the person can actually, or the pilot, because pilot is in the loop and pilot can do the adjustment, the pilot can actually bring the aircraft to a stable position. Now look at conventional control, and there is no fault-tolerant control. See how it happens. We tried to do the same thing. So the system is working normal. Then the similar fault as before happens. The system starts to malfunction, and it takes a while, a little bit longer, for the person to actually bring the system back to the normal operating. And all these are shown as graph over here. So what does that tell you? It tells you the importance of the fault-tolerant controls for safety-critical systems. And you see, it still takes time, but finally, they managed to do that. Okay. So I'm going to stop about this fault-tolerant, and I would like to show you the next slide series very quickly to finish it within 15 minutes or in 15 minutes or so, about how we communicate with the machine and with the external resources in order to monitor the condition of the system. So I'm going to stop my sharing, or maybe, yeah, stop my sharing here, and